Alright, in this video I'm going to show you how we can perform Riemann sums using a for loop in Matlab. So what is a Riemann sum? Just for example, in math terms, this is the way we write a Riemann sum right here. So this sigma symbol with a summation index I, and that summation index takes on certain values in the sum. So this particular sum is saying, hey, sum up the values of f of xi for I equals 1 to 5. So what that actually equals is, here if I write this down here, sum is equal of f of xi from I equals 1 to 5. This is equal to f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5. That's what that Riemann sum is equal to. And I've drawn this little picture of the function here, f of x, to kind of illustrate what that might mean for some function. So now the goal is to show you how you can accomplish that using a for loop in Matlab. So let's switch over to Matlab. So in Matlab, what I'm going to just do is I'm going to define some function that we want to sum over like we did in this example. So I'm going to define a function, some polynomial, okay? So just using a function handle, I'm going to call the function func. It's going to be its name equals at, so I'm using this function handle syntax. So this is saying define this as a function. It's going to be a function of x, and the function itself is going to be, I'm just going to pick x squared as my example because it's a simple function. Alright, so now I've defined this function and I can evaluate that function by typing func open parentheses and pass in a number, so 4, and that returns a value of 16. So it just takes the input and it squares it, as we would expect. Okay, so now that I've defined this function, I'm going to go ahead and write another function that uses a for loop to compute the Riemann sum of this function, okay, of these function values. So I'm going to come up here, create a new function, alright, and I'm going to title this Riemann, I can't remember how you spell, it's like something like this, Riemann sum, and we're going to pass in a function. I'm going to call it f. So that's the function that we're going to sum over, and I'm going to pass in how many function values we want to sum over, and maybe some spacing between the points, dx. So over here in this function that I showed you, I'm going to assume that each one of these points, x1, x2, x3, x4, x5, is separated by some distance, uniform distance dx. So, and in this function over here, I'm going to pass that value in. Okay, so in order to use a for loop to do a sum, you need to create a variable that is going to store the partial sum, or some variable that's going to keep a running total of the sum. So I'm just going to call that variable S stands for sum. I'm not going to call it sum because sum is actually a Matlab function, so that's why I'm just calling it S. Maybe I'll just call it SM. There we go. SM, that'll be my sum variable. I'm going to just set it equal to 0 to begin with. Okay, now I'm going to jump into my for loop. For I is equal to 1, so our summation index here is going to start at 1, and we'll let it go to n instead of 5. Maybe I should just do a simple example and have it go to 5 to begin with. Okay, let's do that. So instead of passing in n, I'm just going to hard code in, it's going to go to 5. Okay. Alright, and then let's also assume that gonna end this. So the very first function value, we also need to kind of specify, okay, what's the first function value here, and or the first x value. So let's just pick I'm trying to think of a simple way to do this. Alright, well, we have the function, so we can evaluate that function at some point. I don't know what point that is yet, but I'm just going to set the summing variable equal to itself plus our function evaluated at whatever point we're going to pick. Well, let's let the first point, let's define a variable that's going to store our x points, and I'm going to define that to be xi. And let's start that out at 0. So we'll start it out here at x is equal to 0. So we'll say this is right here, this is x equal to 0. So we'll start it here and we'll call this distance. This is also dx, okay? Alright. And now in here I just need to calculate that x value as a function of I. So I'm going to say, actually let's just call this this will be the starting bound. So we'll call this xi is going to be equal to a plus I times dx. And then we'll set this to be evaluated at xi. Okay. Now we've got a for loop that is going to actually calculate the Riemann sum for us. And I haven't specified a return variable, but I want to return this summation. And we'll see if it gets the right summation. So let me just save this and run it, and then we'll kind of pull it apart and see how it works. So save this, and then let's go back to the command window, and let's run it by typing in the name Riemann Sum, and then we need to pass it a function. We're going to pass it our function that we defined up here, which is x squared, and a dx value. Let's have dx just be equal to 1, and let's run it. So it says the answer is 55. So let's see if that's the correct answer. First of all, let's actually compute this sum by ourselves by hand. So if our function is x squared, then this summation can be written like this. I equals 1 to 5 of xi squared. So when I is equal to 1, we're assuming these are separated by dx. Then we have x1, which this is just going to be 1. So this is going to be 1, 2, 3, 4, 5. Those are going to be the x values. Right? So this is going to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which that's equal to 1 plus 4 plus 9 plus 16 plus 25. So these two right here are 5. These two right here are 25. And so now we get this is going to be equal to 25 plus 25 is 55. So there's the answer. We did it by hand. So we see that our function is returning the right answer. So how is it calculating that? Let's go back and look at the function itself. So if we break this down, something I can do is I can put a pause statement after each one of my commands. Pause. And pause. And undo. I'm undoing the semicolon so that it's going to output the result. But it's gonna put a pause in between each command so that I can illustrate to you exactly what Matlab's doing. So I'm going to save this, and I'm going to go back to the command window here. I'm going to clear this, and I'm going to rerun my Riemann Sum. Alright, so the very first thing it does is it sets this summation equal to 0. And I'm actually going to dock the command window so that dock the editor so we can see the code here. Alright, so it set sum equal to 0, that's here, and then it paused, and now it's waiting for me to hit a button so it can continue. So I hit a button, and now it says, okay, set A equal to 0. Well, that's what it did here. Then it paused, and now I'm going to hit enter, and we see it jumps into the for loop, and it sets xi equal to 0. So why is xi equal to 0? Well, A here was 0, so this is 0 plus I takes a value of 1 the first time in the loop. So 1 times dx, which dx is 1 because that's what we passed in the value. So this turns to 1. So xi gets assigned the value of 1. Then it pauses and it waits for me to hit a button. Alright, I hit a button. Now it sets this sum variable equal to 1. So how did it get set equal to 1? Well, it says take whatever the value of sum is, which it's currently set to 0 because that's what we set it to, and then add the function evaluated at xi. Well, xi here is just 1, and f of xi is just going to square that. So 1 squared is 1, so 0 plus 1 is equal to 1. Then it pauses. Now it's going to, when I hit a key, it's going to hit this end statement, and it's going to come back up here and execute this again, this first command in the for loop, but now I is going to be equal to 2. So we see xi gets set equal to 2. So A is still 0, I is now 2, dx is 1, so 2 times 1 is 2, that's why xi is equal to 2. And we go on, sum gets set equal to what it what it currently is. So this value is 1 from what it was previously, plus 2 squared. So 1 plus 2 squared is 5, and that's why SM is equal to 5. Anyways, I can hit enter again. Now it's going to come back up here, set xi equal to 3, because I is now 3, dx is still 1, a is still 0. And then it's, can you guess what SM is going to be set equal to? Well, SM was previously 5, and so it's going to be set equal to 5 plus 4 squared, which is 16, right? So 5 plus 16 should be 21. That's what I'm guessing it's. Oh, I messed up. Let's see. Sum was previously 5. And is that right? Oh yeah, we're on 3, not 4. Sorry. So this is 9. So it did 5 plus 9. I'm jumping ahead of myself. So now it's 14. Alright. Now xi gets set to 4 because this is still 0. I is now 4. Dx is still 1. So 4 times 1 is 4. Sum, let's see if I can figure it out this time. So sum is going to be set equal to, previous value of sum is 14. 14 plus 4 squared is 16. So 14 and 16 should be set equal to a value of 30. Yep, got it right that time. Now can I predict what xi is going to be set equal to this time? This time I is going to be equal to 5. So xi should be set equal to 5. And then SM is going to equal 30, is what its previous value was, what its current value is, plus 5 squared, which is 25, so we'll get set to 55. And then that's the last time that we're going to go through this loop because we've reached the ending index. And so it returns the answer of 55. And so the value that it's returning is whatever's stored in this SM variable. So I hope that kind of makes sense how Matlab uses a for loop to compute a Riemann sum. Now, the nice thing about being able to compute a Riemann sum using a for loop is we can perform an approximation to an integral using a Riemann sum. So if I wanted to integrate this function, let me fix this here. Fix this. Stick it up like this. There we go. All right, that looks better. Save that. All right. So if I have this function x squared and I want to integrate it from a to b between these bounds, I can approximate that integral as just a Riemann sum of the y values, or the function, or the x squared values. So this point right, this red dot right here is just this x value squared. This one right here is this x value squared. So on this value right here is this x value squared. So each one of these points along the function can define the height of a box of width dx, or delta x, where this width delta x is just equal to this integration domain b minus a. That gives this distance right here. If you divide it by n, the number of boxes or the number of rectangles, then you get this spacing, how far apart these points are spaced on the x-axis. So this integral can be approximated using this Riemann sum, where this is yi is the function evaluated at xi. Let me write that down right here. So the integral from a to be of f of x dx can be approximated by the Riemann sum from I equals 1 to n of f of xi times delta x. Because this right here, f of xi times delta x, what does this represent? This represents the area of one box. So one of these rectangles, its area is literally its height, which is the function value, times its width, which is the width is delta x. So we can approximate this integral with a Riemann sum, which we can implement in Matlab using a for loop. So let's go back to our Matlab example here, and now let's change this function to actually calculate an approximation for an integral. So let's pass it a function. Let's also pass it the integration bounds a and b, and let's also pass it the total number of rectangles, capital N, that we want it to use in the integral approximation. So I'm going to get rid of these pause statements now. Here. And now I'm going to get rid of this a value. That a is now passed in. And now we just need to calculate our dx value. So we'll set our sum variable still equal to 0. And then I'll set my calculate a delta x. I'm just going to call it dx. It's going to be equal to b minus a divided by n. And then I'm going to have my summing index, or my looping index, go from 1 to n. And now the sum itself needs to be, we don't want to add up the heights of the boxes, we want to add up the areas of the boxes. So to make this an area, instead of just a height, we got to multiply this times dx. So this now represents the area of the box. So I could actually just make a separate variable before this, call it AI, or the area of box I. Set that equal to this f at xi times dx, and then change this just to be equal to the area of box I. Alright, and now this right here represents the approximation to the integral of our function f. So let's try this. So if I let's call it here. I'm going to clear. Oh, I cleared my function. I'm going to redefine my function here. X squared. So let's pick an easy interval to integrate over. One that we can calculate the answer for. So I'm going to pick, let's integrate, x squared over the interval 0 to 4. Okay, so x squared dx, this is equal to x cubed over 3 evaluated at 0 and 4, which equals 4 cubed, which is 64, divided by 3. Alright, so that's the exact answer. So 64 divided by 3, that's what the integral should be when we, that's the true answer to the integral. Now let's call our Riemann sum function, and we changed it now. Actually, I don't know if I've saved it. Let's go back and make sure I save it here. Oh, yep, it's saved. Alright. So I need to pass it a function. I'm going to pass it func, which is our x squared function. A is going to be equal to 0. B is going to be equal to 4. Now let's just use two rectangles. Wow, it returns an approximation of 40 for the integral. The true answer is 21. That's pretty awful. But if you see what this did, the way it approximated it is like this. It said, okay, if this is x, this is x squared, then our function looks something like this, and this is 4. And because we're using two rectangles, we're only having 2 points. And so it says, okay, make a rectangle right here, calculate its area, and then make a rectangle right here, calculate its area, and then sum them together to give me the value of the integral. Well, what are these values? What are the heights of these? Well, 2 squared is equal to 4, and 4 squared is equal to 16. So this right here, the area of this rectangle is, I'm just going to call it A1. A of box 1 is equal to 4 times 2, 8. And then A2, which I'm going to say this is A2, this one's A1. This one is equal to 16 times 2. This distance is also 2. Okay, 16 times 2, which equals 32. So A1 plus A2 is equal to 8 plus 32, which equals 40. That's what our program is calculating. We see this is what it calculates. So if we want to improve our approximation to the integral, we need to increase the number of boxes that we use. And we can easily do that with this function now. I can put in 20 boxes now. Now look at the answer, 22.96 compared to the true answer of 21.33. We're getting a lot closer. Now, how close can I get, and how many boxes can I use? Well, computers are really powerful and fast at doing just basic algebra, adding, subtracting, dividing, and multiplying. So let's use, 2 million rectangles. And there, it spit out an answer that's exact out to 4 decimal places. If you wanted to see more decimal places, you could type in the command format long, and then the answer, you can see it's actually only accurate out to 4 decimal places, because 64 divided by 3 is repeating 3's all the way out. Anyways, there you go. There you have it. I've shown you how to use loops to do Riemann sums and how to do an integration example. We'll see you in the next video.